Welcome to the pre-recording of the first half of lecture 21, scheduled for the beginning of week 8 in our 8-week summer course on computer algorithms. So we are very close to the end. In this lecture, we will consider partitioning problems and show that those type of problems are NP complete. Okay, we've seen bipartite matching. So what is a bipartite matching again? So we are given a graph where the vertices split in two. So there is one set of vertices for which there are no edges between the elements in the set. And there is another set of vertices also for which there are no connections between the elements in that set. So there are only connections between elements of the first set and the second set. One can think of employers and applicants. So the situation where we started with in this course. So then a matching picks one vertex from the first set and one vertex from the other set. So a matching means that you pick every vertex only once. So even if there are applicants interested in for multiple employers, in the end they are ending up with only one employer. No, a matching is perfect if you have complete employment, and this of course can only happen if you have as many employers as applicants, as many applicants as employers. In the bipartite matching problem, this is a natural decision problem, so for any bipartite graph, is there a perfect matching? So we have an efficient solution for this, an efficient algorithm, and that's the Ford-Fulkerson algorithm, which we discussed in an earlier lecture. So the bipartite matching can be generalized to the tripartite matching problem, or in generally more commonly referred to as the three-dimensional matching problem. Now we have three sets, all of the same size, and we see these sets as vertices, sets of vertices in a graph. The sets do not share any vertices. Also, there are no edges between the elements of the same set. And then we are asking for a set of ordered triples where we pick the first element from the first set, second element from the second set, and third element from the third set. With this setup, the three-dimensional matching problem then asks, is there a set of triples so that every element in the whole union is actually contained in exactly one of those triples. So every vertex appears exactly once at the proper spot in the triplets. So this is called a perfect three-dimensional matching. So the three-dimensional matching problem asks for a given tripartite graph, is there a perfect matching? This is a slight generalization, so you can think of somebody responsible for course scheduling, where the first set are a number of instructors, the second set courses. So if there is an edge between an instructor and a course, then an instructor is willing, capable to teach a course. But then there is the other restriction that courses only run on certain time slots. So in a three matching, you must line up the instructors, the courses, and the times. So that is an example of why this is a very important problem. You could also see this as a scheduling problem. And that is an important problem, but a very hard problem for which we do not know an efficient algorithm. So here to clarify the problem, here is an example with 15 vertices, so graph with 15 vertices, where 15 is divisible by 3, so where we have the 3 sets. And then the triplets will be defined by selecting certain edges from the graph. So we can select, if we select the edge 0, 4, then we cannot select the edge 0, 7 anymore. And this then also has consequences. So if we are selecting 0, 4, then we either have to select 4, 5 or 4, 14 to make a triplet. So, and that choice excludes other um, choices of the edges. So if you have been staring at this, you may have figured out a solution. So here is one solution to the tripartite matching problem, or the three-dimensional matching problem. So we have 5 elements in each set. So a perfect matching results in solution set of 5 triplets, where you can see that the first element is divisible by 3, the second element has a remainder of 1 after dividing by 3, and the third element, if you divide by 3, the remainder is 2. So that's the one way to check that one has a solution, that all the vertices are there, so that you have followed the rules. Okay, it's an important problem. So we have seen dynamic programming to organize a systematic exploration of the problem space. So if you pick one edge, then your choices are limited. So you can build up your solution one triplet at a time. So if you pick one triplet, then you remove those vertices. So you go from, in the example 15, you go to 12. And then you do the same thing again. So you assume that if you know how to, so the base case in this reduction, if you have only 3 vertices and they are separated in each set, so then it's quite simple. You reduce it to the case where you have a graph with the number of vertices 3 less. So that's the recurrence. Or if you like, proof by induction, you will set up a recurrence relation and then figure out the time complexity. So there is no efficient algorithm for this problem. So there is no algorithm known that solves this problem in worst case running time. So you can't make any assumptions on the choice of the edges in the graph. So there is no algorithm known that has a worst case that's bounded by a polynomial in the input size. So you should actually not find a polynomial time algorithm if you apply dynamic programming, but it is nevertheless an important way to see how you reduce the problem to a smaller problem, but know that you essentially have to consider all the edges as the first possible edge in your connection of the two graphs. So that will, so the number of combinations will make that problem rather hard. Okay, how to now show that we can that this problem is an NP complete problem. So if we would find an efficient algorithm for the three-dimensional matching, then the distinction between the set of problems for which we have efficient algorithms and the set of problems for which we have efficient certifiers, that distinction would cease to exist. So it's very similar to the set cover problem. The set cover problem starts with a collection of labels, and you select from those labels or from those n first natural numbers. You select subsets, so finite in number, and also another number k, and then you ask, can you cover the entire set of the first n natural numbers by the union of your selection. So we have studied the example, that problem in the first lecture of the week 7. Uh, an application for that was that the set of U was a set of capabilities, and then the S was a collection of softwares that were capable of that were offering those needed capabilities. So we reduced tree satisfiability in polynomial time to set cover. Tree satisfiability can be reduced to circuit satisfiability, and we've shown that a circuit satisfiability is the most general problem because you can encode any circuit as an algorithm, a conventional algorithm on a computer, on an electronic circuit computer. Okay, so we are going to set up a reduction showing that tree satisfiability can be reduced to the three-dimensional partition problem. And the way we're going to encode these problems will actually use ideas of set cover. So you can actually see here that we consider all the vertices as that set U, and then we have to find sets of triples, n triples essentially. Okay, and this covers it. First, let us recall what is now the general strategy to show that a new problem, for us the new problem is the three-dimensional matching, that is an NP complete problem. So first we must show that we can verify that any collection of n triplets is actually a solution to the problem that solves the three-dimensional matching problem in polynomial time. So we call that an efficient certifier. That step is typically straightforward, part of the basics. What is not so straightforward is actually choosing a good problem that is very similar to the problem for which you can intuitively see that that NP complete problem can be reduced in polynomial time to your new problem. And then you have to do the work. If your choice was good, it will work out fine. But you have to explicitly exhibit an algorithm that rewrites the input instance to the known NP complete problem in the input of your new problem, and also show that the solutions are actually equivalent. If you have solved your new problem, then you also have solved the NP complete problem. And the NP-complete problem solution also has a very natural interpretation in the output of your new problem. Okay, we have actually so the relationship between three-dimensional matching and set cover is not hard, but actually we want to do the other way. So we have to show that the NP-complete problem can be encoded as an instance of a three-dimensional matching problem. And that's for any problem. And we only can use a polynomial number of operations, of elementary operations. So that's a restriction. So in some sense, you could view what we're doing in this course as the design and analysis of algorithm. In our analysis of a problem now, we are designing an algorithm. So everything is fairly constructive. Even though we use the language of mathematics. So if you actually don't really like this approach, you could spell out explicitly in pseudocode how you would verify that a set of tuples, that set of tuples solves is the three-dimensional matching problem. How would you do that? Well, we have to make sure that all the points that occur in these triplets actually result in the entire set of vertices in U. And you can do this by having a Boolean array of 3n, and each time when you encounter a number, you mark the false to true. If it's already true, then you have a duplicate. If at the end there are also certain things that you haven't encountered, or if there are gaps, then you will also notice. Now the importance is this can be done in 3n. Now you have to make sure that if you have a triplet, you have to make sure that there is an edge in the graph, and there are m edges. So assuming that, again, you just have the plain list, if you have an adjacency matrix, this would happen in constant time. But we are satisfied with a plain polynomial time algorithm that for every triplet we check whether there are edges between the selected vertices. Okay, so we have thus shown that we do have an efficient certifier, even if we don't really know how to efficiently find the three-dimensional matching. But this is good also for a non-deterministic algorithm. Also very good to check if you have solved your first exercise, that actually automatically, that you can do very quickly, that what your algorithm returns actually will be a correct solution to the three-dimensional matching. Okay, so let's now do the hard work. So we will reduce this problem to finding triplets. So here we have a collection of triplets. We will reduce this, we will show the equivalence with the tree satisfiability. So in some sense, tree in tripartite graphs, in three-dimensional matchings, in tree satisfiability, it is quite intuitively clear that the problems are kind of related. Keeping in mind also the set cover. So what do we construct? We construct triplets, we consider triplets, where we have for a collection of 4 triplets, we have 8 different variables. One set of variables we call the A's. They are the core of the gadget. So we are constructing this diamond is referred to as a gadget. We have the core of the gadget, and then we have the tips. So we have to cover these 8 elements by triplets. And we have to make sure that always the core is covered. So to cover the core, we can do this with 2 triplets. So the covering will be kind of specific. So we distinguish between triplets where the last element, the last index, is even. So the first triplet ends in B12, 2 is even. That's thus an even triplet. The next one is an odd one because 3 is odd. Then we have an even one again with the 4, and then we have an odd one again. So the labeling here happened um, clockwise. If we run over the tips of this gadget clockwise, then what happens is that if you assign to if you consider in a covering, you select 2 triplets, so you have to cover the core. If you select the triplets that are even, then that corresponds to an assignment to 0. If you select the odd ones, then you assign the corresponding variable to 1. So you may have wondered why this double numbering, double indexing. Well, we are here considering only one variable. And we have 4 possible triangles. So here in this picture, we see the 4 triangles where every triangle corresponds to a tuple in T. Okay, so like with the Hamiltonian cycle problem in the previous lecture, how much information can we encode in such gadgets? It should be sufficient for a tree satisfiability problem, and it should actually, the size of all these triplets, it should actually be polynomial time. Um, so let's continue here. What happens if we have 3 variables? So then we have 3 gadgets. So the first index of the variables, the core and the tips, the first index corresponds to the corresponding variable. And you see, of those 8 letters, of those total 8, we each time select 2 triangles that cover the core, depending on whether we want to assign to the variable 0, 1, or 0 here in this case. Okay, so in total here we have 12 variables, or 12 is the total number of triplets. How much information can we cover with this? How much information can we store? Well, we can store the result of 8 different assignments, 8 being 2 to the power 3. So here in red, I indicated the assignment 0, 1, 1. And actually, I should have indicated in red 0, 1, 0, because that is the example. But nevertheless, the point is that you can encode the entire truth table with 12 triplets, or 3 sets of 4 triplets. The slides would not permit a truth table of 16 with the completely spelling out of all the triplets. But you can see that if we have one more variable, we're adding 8 more letters, or 4 triplets, but the number of rows in our truth table doubles. So here we have 12, then we will have 20, but we can make 16. From 16 we go to 32 by adding yet another 8. So the doubling grows way faster than adding another 8. So you can see that the information that we can store by these triplets actually grows exponentially. Each time when we add 4 more triplets, we are doubling the amount of information that we can store. Okay, how do we now encode a tree satisfiability problem? Um, what is a tree satisfiability problem again? We consider a collection of clauses where every clause consists of exactly 3 terms. So here is an example of such a clause. So we have the 3 variables x1, x2, x3. So we have the corresponding gadgets, and we can represent the clause. So here the clause of the 3 triplets that actually makes this work. We have to choose one of the tips. So in green I indicated the obvious choice of x1 equals 0, x2 equals 1, and x3 equals 0. Now, in order to make the clause make true, you don't have to pick all 3 green ones. It suffices that one is picked. But you have to allow for the covering of all the tips. So that means that you have to have in total 8 triplets. So you have the 3 triplets that come from the clause that give you the 3 possibilities that make that clause become true. But then you also have the 3 ones, the 3 in yellow. But you have to make sure that it suffices that only one of them becomes uh, that only one assignment, because it's an or. If x1 equals 0, then the clause is true even though x2 may be 0 and x3 equals 1. So you have to allow for those possibilities. So we have now the clause that is represented by these 3 gadgets for the 3 variables. And then we have the 8 triplets. So the 3 gadgets each represents 4 triplets. We are adding 8 to them. Okay, so the reduction is a little bit heavier than what we have covered before, but it will be polynomial in the input size. So the input size is the number of variables and the number of clauses in our tree satisfiability problem. Here again, if we have 3 variables, we have 4 tuples, 4 triplets for every variable, so 12 in total. Then we have the triples for the clause and the triples to make the matching perfect. So in total here we have 12 plus 8, 20 triplets that will encode the tree satisfiability instance as tripartite matching. Okay, so here is then the full description. So what was the input again to the tripartite matching, or to the tree? The input was a tripartite graph given by the 3 sets. Given by the 3 sets, but then you also need to define all the edges. And the edges are actually defined by the corresponding um, triples. So you have to make sure that for that if you want to select B12, there would be the edge there. Okay. that's then it. So there is an algorithm here. So in the tree satisfiability problem, we have a number of clauses. So here we have k clauses, each of 3 terms. We have n variables. So for every variable, we have these 2 sets of letters, and then the set of triplets. So for every clause, we have a systematic way of adding 3 triplets, depending on whether the terms correspond to the original variables or their negation. And then we have the extra um, triplets that we need to add to ensure that the covering, the matching will be perfect. Okay, so this gives then the total number of triplets that you need. So you could say it depends on the number of variables and it depends on the number of clauses. So adding everything up, we have a total number of triplets that is bounded by a polynomial in n and k. Then we have the even and the odd triplets that contain the core variables. And then all the elements that are the last element of the triple are all the bj's. So you can verify that the set x, y, and z, they actually are of the same size. Now the algorithm on the previous slide runs in polynomial time. So the input of the tree satisfiability problem that is encoding the tree satisfiability problem is also polynomial in size of the parameters number of clauses k and the number of variables. Okay, here is then the exercise. So if there is something that you must retain from this lecture, that's the central idea, if you like. How can you now encode here an instance of the tree satisfiability problem as a tree matching problem? Also show, and that comes then to the next stage, demonstrate that one is actually equivalent to the other. So if you have your truth assignment that makes this collection of clauses yield the value true, that actually then also in the three-dimensional matching, you do have a selection of triplets that represent a perfect matching. And actually, we're interested in the opposite. So from your perfect matching, how can you read off the truth assignment? Okay, so we're going to formalize this. Um, the proofs actually are now quite short because they incorporate the logic of the explanation of the encoding algorithm, which is outside of the proofs. So the textbook has very long proofs, and that is necessary if you want to be self-contained. So here in this lemma, we indicate that if we have a satisfying truth assignment, then we actually know which triplets to choose. Now that actually means then if we have a solution of the tree satisfiability problem, we actually will cover the core of everything, and we also will select at least one tip. And then we have sufficiently many added triplets so that we have still sufficient room for a perfect three-dimensional matching. So from an assignment, we can actually select there the the triplets that give us the perfect three-dimensional matching. That's one direction. Actually, that's the direction that we defined in the algorithm. What we actually are after is actually the opposite. So if we have a black box that solves the three-dimensional matching, we have to be able to show that our three satisfiability problem has a truth assignment that yields 1. Okay, so what happens if we have a three-dimensional matching problem? Note that we do need to cover the core again. So we have then either selected all the even triplets or the odd triplets. And that defines a 0 or 1 assignment to the variable. And the fact that we had a perfect matching, we didn't skip any of the clauses. So for all the clauses, we actually will end up with a satisfying truth assignment. So we will actually cover one of the tips that makes the clause become true. Dilemmas are short, but they refer to the correctness, in essence, to the correctness of the encoding algorithms, which have been introduced by the examples. Okay, now the main theorem, the first main result of this lecture and the main result of this first half of this pre-recording. So we showed that we have an efficient certifier that makes that a three-dimensional matching problem belongs to the set NP. And we have shown that an arbitrary, so any arbitrary collection of clauses, so we have solved the exercise 2, that can be reduced in polynomial time to the three-dimensional matching problem. So that is the correctness of the encoding algorithm. It runs in polynomial time. Actually, not the correctness. I should have framed also a little bit more precise the polynomial here, the polynomial expression in n and k. So by dilemma then, the problems are equivalent, so by the last lemma. So we have polynomial reducibility, and not only that, we have the correct interpretation of the outputs. So this shows that the three-dimensional matching problem is NP complete. Okay, to conclude, let me mention another partitioning problem. That's the very important graph coloring problem. So you want to color a graph with as few colors as possible. So again, it is essentially an optimization problem. So adjacent vertices should receive different colors. So if there are no edges at all, then one color suffices. So that's a trivial case. But it's a hard problem to actually decide whether three colors suffice. So you can also see that the two coloring problem, if you have a bipartite graph, then it's obvious that the numbers, the vertices in one set, you have one color, red, and then green for the others. So one version of this theorem is straightforward. If you have a two colorable graph, then you can actually reorganize your vertices. So in sets of the red and the green ones, and it will be a bipartite graph. So this theorem is actually very straightforward to see, and it illustrates that this is essentially a partitioning problem. Now, I don't want to trivialize the subject here, so there is an entire subsection in the textbook that deals with the reduction of tree satisfiability to tree coloring. And that actually then shows that tree coloring is also NP complete. Now, the goal of this course is that you can read the textbook on your own. So, in some sense, this is an invitation for you to study more about this problem, an important problem that also concerns compiler designers who have to somehow divide up the registers. So, this is a very important practical problem, but it is a hard problem. So you can't really expect to do this for an arbitrary number of growing dimension and still expect that your running time actually grows um, according to some polynomial. Okay, so that is the end of this first pre-recording. We will continue in this next pre-recording by considering numerical problems, which is a different category of problems for which we will show that we can reduce three-dimensional matching to the subset sum.